Hello everyone, we just released MLatom 3.2.0, which is a major release with many new features, usability and performance improvements, and bug fixes. In short, we implemented energy-weighted training of any machine learning potentials, which can be useful for cases when you have a global potential energy surface and it is difficult to treat different regions of potential energy surface on equal footing. You can check out for more information about why it can be useful to you in this preprint, which we just also recently put online. And the idea is that different regions of potential energy surface need different weighting when you calculate the loss function with machine learning potential during its training. We also provide some tutorials for it, which you can check on GitHub, and also there is a Jupyter notebook. So in a nutshell, you just need to provide a weighting function and some parameter for this weighting function, and then you can train your model by providing the weighting function as an argument to the model training. Also, for the same project, we implemented interface to diffusion Monte Carlo software, and now you can run diffusion Monte Carlo calculations with MLatom 2. That provides you accurate frequencies and 0-point vibrational energies. And since these calculations are very slow, you will benefit from many different machine learning potentials, which make it faster. In addition, we improve our old implementations. For example, AIQM1 on the cloud, it had some numerical problems, so we tried to improve it as much as we could, and now you can have better stability. So you can give another try for AIQM1 on the cloud, and then you can also run here on the cloud computing calculations. There is also Jupyter Lab, and you can try yourself different tutorials, like here MLatom tutorial, and it provides you also some examples for AIQM1 calculations. Here to know that geometry optimizations are okay, much faster. With frequencies you need to be a bit more careful because we use numerical differentiation on the cloud. So locally you can install a MNDO program with analytical gradients. Now we also implemented interface to PySCF, which provides quite robust solution to calculating frequencies and thermochemical properties. You can try it by providing an option like this, and then it's enabled by default if you don't have Gaussian. For other improvements, we did better interface to ORCA, so you can run some DFT calculations with ORCA, for example, and we made calculations at couple cluster calculation level for charged and open shell species also available, which was not available before for some specific extrapolation scheme. Another feature which might be useful for many computational chemists is that you can do geometry optimization with constraints. Now also on the cloud, when you use interface to ASC, and we provide here also examples, and at the end, if you want, for example, to fix carbon-carbon bond lengths during optimization, you can successfully do it and then get the final geometry satisfying your constraints. So we hope that you will enjoy this release, and we are working on further improvements. So if you have other suggestions, you can let us know in the support channels as usual.